what does it mean? Two graphs. Graphs can only be equal. Exactly the same edges. Not really what we're using as our definition, because we drew the same graphs several different ways. The question is, how do I know structures are exactly the same? Okay. Word isomorphism. Isomorphic. Even if it's labeled, and we write isomorphic with a wavy equal sign, UH. Isomorph means shape. So isomorphic means same. Isomorphism in other classes, but places. 5 graphs. So 3 graphs of order 5 and some equal graphs. That first, what's the name of that first? H1, because that's a structure. No, it's got a name. A cycle of size. If that's 5, my question really is this size? I've drawn. I've got edges crossing in all sorts of different places. But we said earlier that the way you draw a graph is completely fungible. I can mess with that all I want. So it's the same if I can relabel 2 in a 1-to-1 function H1 and preserve adjacency. Pardon? G isomorphic if a function from the vertices of G to the vertices of H one-to-one and onto UV an edge if and if the edge that you create that are a G have to be adjacent in H. Now this sounds all in my mind. I claim that the 5 and the star that I've called H2, I claim those are the same. If I show that, then what I have to do is I have to from the set U1 so the things that are adjacent to H1 adjacent in H2. What function values? Let out explicit. Even write it over. U. What is the image of U? Where does it go? If I'm on U2, then the things that are adjacent to U1 need to become the things that are adjacent to U2. So, do you want to go left or U1? If I'm going left, Y1. Y1's adjacent to U1. Whatever Y1 has to be something. Okay? So Y1 goes to 2. Do you want to go there or do you want to keep 1? You have your choice. But if our goal is to way counterclockwise around here, consistency from Y1 to X1. So from X2, I can't go back to 2. I've got to go to 2. That X1 match with V. At X1, go back to Y1 to W1 to X2, the other direction. So W1 has to match to Y2. And that means that last but by V1 go. Now notice, observe adjacency. H1. W1. To Y2 over here. In fact, if I number the edges, edge 2, edge 3, edge 4, and edge 5. Then look at their images over on the side. I could say this edge from U to X2, that is the image of all the images of my edges out exactly the same. This looks awfully pixelated to me. I think I'm on the camera wrong. I'll undo that in the screen. So I apologize for the blurriness. I post the picture of my papers so that you get the less blurry things. I'm sorry. Question. What about H3? Is it the same as one? Or is it different? If I remove those when I twist it over, which means you know what the between 1 and H. Will go to U. Y will go to V1 will go to V3. And the only thing you have to do is close. X1 goes to W3 and W goes to X3. The twist you wanted. So my map has to be 1 to 1 on, right? So I have to call all 5 1 to 1. So my map F1 is U3, F of Y1 is Y3, F of V1 is V3, F of V3, and F of W is X3. My function 1 to 1 on. The sorts of pictures back in the diagram. Been a long time, people. If labeled, then 2 graphs for any labeling them, and then that isomorph be built. And Ben, you're exactly right. Mentally, I can look at the really the same picture, moved crap around. And if they're the same foundation, same graph. To determine. Correct. Then we are graphs we can draw of order one. Everything is isomorphic of those. How many graphs are there? How many distinct graphs of order? one? 3 or 4? What are they? Well, if I've got 3 vertices, I could all 3 edges. What else could I have? Here's the best part. Which one I leave? I could just rotate the. Which 2-edge triangle you pick, it's going to look like. What's the other? And again, if there's one edge I keep, I just put it on the left. Now it goes up. Possible I could put down, right? Started with no edges. Put 1. I could put 2. There are for each edge. Either it's in or it isn't. If I go with the straight application, but all 3 are isomorphic. With vertices. All right. There are 8 pictured here. So what is 4 vertices? Start drawing. I have 4 vertices. What is the most? That would be 4 all the possible edges, right? 4. Edges in or out. 2 to the 6th is 4. Right. That's a lot of abilities, isn't it? Even the next 4 of them, step would decide which ones were isomorphic. Else triangle. Six, 15, 15. What is that? One graph with, there's 6 graphs with 1 edge. There's 6 with 2 edges. 21 for a while. 87. All is said and did all 4 and then broke them up. This no. Right? Either those two edges are both into a converse or they're not. Two different ways to draw this. Draw that. How do I know different ways to draw this? And if you could upper left, or lower right. And how do I know there are two ways to draw the other one? Well, when you get here and you start end up being 15 of those, I can do that. I don't want to waste your time, so I'm not going to. Because larger graphs, even if we know they have the same number of edges and the same number of vertices, so here are two graphs on 4 with two each, and they're not isomorphic. If either the size of the edge set, the graph, the size of the vertex set is different. And why would it should, but why would they not in this case? Or is there another way that isomorphism? It's either not if it's G, then I've got a smaller thing. I've got to hit them once. Coming from small. When the vertices are the same size, what is the size but the edge isn't? which one is bigger? The set of edges E doesn't have an image A. If the set H is larger, set for H, the G. And remember, a one-to-one function has an inverse. Go the other way. So, at the same size, we broke the one-to-one and onto part. And if the edge set are at the same size, we isomorph. Those are abstract. I'm using in terms of the option. It's the same finish. F prime has 4, double prime has 5. H and H double prime both have 6. So is possible that edge count 1, 2, 3, 4, 7, 8, 9. 1, 2, 5, 6, 8, 9, 10. 5 on the top diagonal. Written it as, which means we should read it to complements. Okay. This proof is about 2 sentences. Is this true?
We'll say like G is not.
Right.
H. The complement of H is whatever that.
This is the problem. We have to be able to get our.
So if there was whatever number of vertexes in G, the complement have the same number of vertexes in the it doesn't G.
So complement. G complement means the edges that G doesn't. Okay. Excuse me. Say that again.
H doesn't.
doesn't. Edges that are from H are the missing. When you over to the complement, those are the edges that show up in H complement. We go right back, and instead of is in, we use if the edge is not in G, and it's not in this one, it must be in the complement. Two sentences. Think of it as when I map things that are adjacent to things adjacent, I'm mapping things that aren't adjacent. When adjacent, they must now. Oh, nope, that's not Y. That's U1. V1, Y1. Graph. From C. How many vertices in H1? How many? So order size 9. What about K? Ben? Three coming, three coming, three coming down. Three going up, three up. 18. 9. And there's still 6 vertices. 3 on the top. So these have the same size and same order. Are they the same? Are they isomorphic? A lot of stuff. So what if instead of looking at we look at complements? It's easier to do the complement. So what is a clearly I need this and this edge. What's I need those. This, by the way, copies of C3. The triangle on top, triangle on the bottom. Looks like D's to me. What's H1? Pick a place to start. If I start from X1 is connected to V1, V1, and U1, which means in the element, W and Y. Those are the edges that are not. Pick another. U, Y, now pick another. Y, which one do you want to start with? One? Z, Z. Start with Z1. That's X1. It's got to go to U1. U1. Uh-oh. What's my problem? Say again? I. Well, technically, it's a circuit, right? Not even close. By the way, if I do the edge that's missing, that, there are a number for the element. That's a cycle, separate cycle 3. Complements are isomorphic. The original graphs be isomorphic. Another way to another way of acting isomorphic is by part 2. What do we know about every part-type graph? What's contained in, or more precise, isn't. We stated this explicitly back in chapter. Actually, back in chapter. Graph is by part. It contains right. And in this case, rho V is the bottom set. 4. Something else it contains. Well, type set that stick with that. Contain any odds back and forth between the part-type sets, right? The edge has to go back. I have to do it in an even number. Graph on the left contains a triangle. That's an cycle. On the right contains no cycles. They can't. Can't have a triangle. Here's another way to examine isomorphism: structural properties of a graph, difference between one and the other. It's the idea of having an odd cycle. On the through. Later, get to it, draw a graph without crossing any of it. Drawn edge from Z to W just as easily have drawn outside and thus not cross anything. Never be drawn without ever. There's another structural property that's different. In the course of time, we will examine several structural properties, and we'll say isomorphic graphs have to share this property. Unfortunately, there is no property sufficient guarantee that a pair is isomorphic. All graphs with the same number of edges that drawn flat crossings might be the same. That's just not. Isomorphic complement. Now that will work if we are the total maximum number of I could have. But if I want to set the G complement, those, right? I have to count all those either in G. Half of them in G. With a little modular divisible by 4 congruent or 1 mod 4, not 2 or 3. Which means I can't do this 7 on 5. I can't do this on 11 vertices. I can't do it on 12. This number has one of these two. Four vertices. I what's the complement of that? Where do I put the on G bar? I'm going to label these. As G. I'm going to label these. The order is the same. Three connects to one, one connects to four, four connects to two. Graph is self. Stas earlier that the degrees had to theorem. We should be able to prove it. Again, this is a fairly short proof. How do I prove that V have the same degrees as the vertices in H? I have this vertices. Think about what that map does. Pick any vertex over here. This vertex has a neighborhood. The definition of isosurfaces preserves the efficiency. That means every edge over here connected to this vertex U has to be that's connected to this vertex phi of U. But that means the number of coming out have to match the number of things coming out over here. That's the degree of this vertex. That's the definition of this. It preserves adjacent. It's got to preserve neighborhoods. That to tell them not to start two graphs on page 8. This theorem. See you all then. Have a still trying to figure out what